Hello folks, we're gonna measure the distance to the sun using a solar power meter right here. Simple piece of electronics. We'll point it at the sun as it moves throughout the day, and we're measuring the direct normal irradiance. After a long winter, springtime delights with color and fragrance. As the sun rises higher and higher in the sky, life just explodes. I began to wonder whether I can measure the distance to the sun by using the inverse square law. The solar irradiance is about 1,000 watts per meter squared, and the whole industry has sprung up around this energy source. The National Renewable Energy Laboratory has a number of online resources, including maps. Instead of using my own data, I decided to use publicly available data, as you see here. So I took this chart and extracted the data and plotted everything out. I primarily focused on the data from Teide Observatory in the Canaries. Very beautiful place. This observatory is located at about 2,300 meters above sea level. And if you don't know where the Canaries are, they're off the western coast of Africa. So let's have a closer look at the data. I primarily focused on Izana from the island of Tenerife, okay, from the Teide Observatory, because it has the highest power levels, right? So this data, as you can see, was captured, they're monthly averages, but they're captured on clear days, okay, with hardly any clouds, and that's important because the atmosphere will attenuate some of the energy. And so we see 2 months here, January and July, and it's very interesting that in January the intensity is higher than in July, and you'll see why that is. I'll show you everything. And yeah, so I digitized this data using an online tool and put the data in a spreadsheet and began doing calculations, which I'll show you. Just incredible what we can deduce from this simple graph, so stay tuned. So here we go, let's get into it. So it's a busy spreadsheet and I cover some things up so I can focus your attention. So let's focus on the graph data on the left. That was extracted from the graph, and you can see a plot at the bottom, okay? Now, as I mentioned before, we need to pair up the data with azimuth and elevation, and for that I used the Naval Observatory website, okay, to extract that data, and I offset for UTC, etc. And using the elevation, I can calculate the ground range. But hold on a second, how do I know what the slant range is? And that's where the magic is. I used the inverse square law, okay, and I postulated a total power of the sun, as you can see in the spreadsheet top left, okay, and I matched the horizontal distance, the yellow highlighted box, okay, with what the globe predicts, where the sun is exactly overhead at the zenith. So obviously I'm doing that because I'm postulating a flat Earth. So this is in a coordinate that's centered on Izana. Okay, so if you believe in the globe theory, this would be like a plane that's tangent and touches the Earth at Izana. Okay, so that's what this is, and we're gonna plot this in a second, and it'll blow you away. Here's the data, folks, just incredible. So I uncovered the chart on the right, the big one, and notice the greenish bluish curve, that's the data, and then I put a curve fit on it, and that's the actual path of the sun measured with this technique. Now it's very interesting that initially it appears the sun is coming from far away and then rapidly adjust to this curve, and that's due to refraction and attenuation in the atmosphere. The elevation angles are very low, and there is a lot of propagation to the atmosphere and dissipation of the solar energy. So it translates into a distance, okay? But it's not accurate. So right when it joins the curve, it's about 15, over 15-degree elevation, and that's when the data becomes extremely accurate. So look at that, just a perfect curve around the world. And we'll project this because right now it's kind of confusing. It's got two different radii. At the closest approach is about 5,400, and you'll see that at a certain angle towards the east, it's got a much larger radius. So remember, refraction in the atmosphere and in the curved space-time plays a big important part in giving us the globe illusion. If you've been following my channel, you'll no doubt have heard me say that a few times. But let's look at this spreadsheet right above the curve fit box. I have some data up there. So R is the radius of the curve fit from the North Pole. And then below that, D is the distance of Izana from the North Pole. And notice it's about 9,000 kilometers. And it doesn't quite jive with the distance derived from the globe, just the surface distance, unless we apply the 4/3 R approximation, which hints that refraction has been shrinking the globe. So this is just incredible, folks. When we plot it on an azimuthal equidistant map, we can see the path that it goes around the North Pole. Just incredible. If we do the same thing on a globe, there's gonna be issues. Yeah, not quite what you expected, did you? Yeah, the world is very mysterious, and it's very exciting to use all the tools at our disposal to figure out exactly where we are, because the globe is one of the oldest things we haven't discarded. It was developed in the visible spectrum by the Greeks that lived in very sunny areas, and we're still stuck with it in this space age, which is incredible. The globe is an archaic model of the world that's been disproven by science over and over. And you would think people would be shouting that from, the educational pulpits, but they don't, because a lot of people are just taught the old theories. The Almighty has warned us not to walk by sight because we will be deceived. There is light bending, and a lot more mysteries. And I will bring you those as I have time. But let's have a look at the July data as well. Here the effective radius of curvature is 10,000 kilometers. The sun is much closer to Izana. And also notice that when we curve fit the data, we got a lower effective power, total radiated power by the sun. Again, we mesh the yellow cells to make sure we get the same distance. And it makes sense because during the summertime there's a little bit more moisture, right? Temperatures are higher. Still, the data was taken on clear sky conditions, But yeah, now the elevation is much higher and the path is very nice and clean. So just incredible results, folks. But why is there a difference in powers? Well, I've been following and studying the sun with my telescope. I have a 8-inch Smith Cassegrain with a solar filter, and I've been taking lots of pictures of the sun. And here you can see the difference between December time frame and June, July time frame. There's a noticeable difference, and this is done at the same elevation angle, I believe. There is a difference, and there's also a difference when the sun rises. You know, there's refraction, magnification, but also the sun gets closer and then farther away. So there you have it, folks. Just incredible. But folks, there is something very dangerous in this picture. What if the sun deorbits? We've seen anomalous, perhaps supernatural intervention around our sun, and over the years there have been these drastic drops in CO2 that we've uncovered from cores in Antarctica. Somebody is intervening. I hope you all know the real sun, the real life giver, the Lord Jesus Christ, because folks, he is coming back and he is the only way to salvation. God bless you all and stay true to the faith.